so let's continue with subject material on linear transformations. If I have a linear transformation from a vector space V to a vector space W that is a one-to-one map and it is onto, right, then a linear transformation such as that, right, is called an isomorphism. Okay, so let's see an example of an isomorphism, right? I have vector spaces P2, right? So this is polynomials of degree at most 2, right? And I have vector space R3, right? Which would be vectors with 3 components, right? Set of vectors with 3 components. Okay, and I'm gonna illustrate that these two over here, P2 and R3, are actually isomorphic, right? So let's actually start looking at the elements, right? So this over here, this 2 plus 3t plus 5t squared, right? This is an element of P2, right? This is a polynomial of degree at most 2, right? Of degree 2. Okay, now, so this is a polynomial in P2, right? Now, let's consider this 2, 3, 5, right? This here is a vector in R3, right? Now, if you're looking at this element here, this 2, 3, 2 plus 3t plus 5t squared, right? Remember what your polynomials, what the powers of t it's doing for you, right? It's indexing your coefficients if you want, right? So what I mean by that, right? So the constant term here is 2. The coefficient of the t over here is 3, and the coefficient of the t squared over here is 5, right? And those don't interact with each other in a polynomial, right? Well, just a polynomial by itself, right? Okay, so you could regard the powers of t as really being placeholders for your coefficients, right? So for this t over here, you have a 3 associated to it, the t squared, you have a 5 associated to it, and for the constant term, you have a 2 over here, right? So what I'm saying here is this 2, the information in this polynomial, provided you write it in this order where you have constant term, then t to the power 1, then t squared, right? So if you write it in that order, really what tells you what this polynomial is the constants, right? The 2, 3, and 5, right? I notice I can record the 2, 3, and 5 over here, right? And likewise for this polynomial here, which is 1 plus 0t minus 2t squared, right? What I can do is I can record the 1, the 0, and the minus 2, right? The 1, the 0, and the minus 2, right? So what that does for me is that in fact gives me a way to go from a polynomial, right, to a vector. All you're doing with the polynomial is, provided the polynomial is written in this form, right, constant term, term in t to the 1, right, and term in t squared, right? Then a polynomial like this, what you could do is you could write it as a vector by just taking the coefficients 2, 3, and 5, like this over here, right? So in general, for a polynomial in P2, which I can write as a plus bt plus ct squared, right? I can extract the a, b, and c over here and just write it as a row vector, right? Okay, so notice what that does, right? That in fact gives me a map from polynomials of degree 2 to vectors with 3 components. It gives me a map from P2 to R3, right? And this is how you define the map, right? For your polynomial, you just take your coefficients a, b, and c, and those form your components of a vector, right? Okay, so far what we have is a map from P2 to R3, and we have a way of identifying a polynomial in P2 with a polynomial with a vector in R3, right? Okay, so now, well, these are vector spaces, right? So you also have a vector addition and a scalar multiplication, right? What we're going to see is this map over here, right? It respects the vector addition and it respects the scalar multiplication, right? In other words, this map over here is a linear transformation. But less formally, let's see over here, right? Okay, so I have this polynomial here, 2 plus 3t plus 5t squared, which I can identify with the vector 2, 3, 5, right? And I have this polynomial over here, which is 1 plus 0t minus 2t squared, which I can identify with the vector 1, 0, minus 2, right? And notice when you add the polynomials here, right, what you're doing is you're adding the constant terms, you're adding constant terms, and you add in the coefficients of the t, so you get 3 plus 0, which is 3 over here. And then you add in the coefficient of the t squared, so you get 5 minus 2, which is 3 over here, right? Okay, so what you're really doing is you're just operating on the constants, right? So notice over here, well, if you want, this 235 is recording the constants in this polynomial, right? The 1, 0, minus 2 is recording the constants over here, right? And when you add, all you're doing is you just add in corresponding components, right? So basically, this vector addition, I can actually just write in this way over here, right? In R3, right? So what I'm saying is that this operation of polynomial addition is really basically the same sort of operation in of vector addition in R3, provided you interpret it correctly and so, right? So what you're doing over here, it really doesn't make a difference if you write it as a polynomial over here as you write it, or if you write it as a row vector, right? You really just doing the same thing, right? You just add in the constants. For example, 2 plus the 1, and then the 3 plus the 0, you just add in the constants, yeah, and likewise you add in the constants over here, right? Okay, so in that sense, the P2 is behaving just like the R3, right? And that is illustrating what the isomorphism is, right? The isomorphism, the behavior in P2 of the elements in P2 under addition is really just the same as the behavior of the vector addition in R3, right? It's just a different way of writing things, right? So going from P2 to R3, what you're doing is you're just relabeling everything, but it really just has the same sort of structure, right? So that's an idea of what an isomorphism is, right? An isomorphism, this is a particularly nice and simple isomorphism, right? But an isomorphism between vector spaces, what you're doing is you're just essentially just rewriting the vector elements in a certain way, right? So that the vector addition is preserved when you go from the first vector space to the second vector space, right? And similarly, the scalar multiplication will be preserved, right? So for example, if I have this polynomial here, which is 1 minus 2t plus 5t squared, and I multiply by a scalar 3 over here, right? Well, how do you do this, right? What you do is you just using your usual multiplication of a scalar by a polynomial, so it's going to be 3 times 1, and then 3 times the minus 2, and then 3 times the 5, so you get 3 minus 6 and 15 over here, right? So 3 minus 60 plus 15t squared. I notice that's essentially the same thing that what you were doing for scalar multiplication inside R3, right? You'd really just multiplying the components over here, each one by 3, right? Okay, so what you're doing across here in the polynomials for your scalar multiplication is really just the same thing as what you're doing across here in R3 for the scalar multiplication. You're just writing it in a different way, right? Okay, so both the vector addition and the scalar multiplication, they behave the same way in P2 as in R3, right? Okay, so right, so that's an idea of what an isomorphism is, right? But formally, what an isomorphism is going to be, right, is what you'd want is, first of all, you'd want the identification, right? Okay, so the identification is, well, how do you identify the elements, right? Okay, how do you identify the element, say, 2, this polynomial here, 2 plus 3t plus 5t squared with the vector 2, 3, 5, right? Well, how you do that is formally you have a map, right? So you have a map from a polynomial of degree 2, right? And all you're doing is you're just taking the respective coefficients of constant term in t, and term in t squared, and you're forming a row vector over here, right? Okay, so first of all, for isomorphism, you need the map that takes you from vectors in P2 to a vector in R3, and this is the map over here, right? Okay, so now this is just a map, right? Okay, so this is the map, and over here I say that I call the map from P2 to R3, I'm going to call it big T, right? So the map big T is taking polynomial a plus bt plus ct squared to the vector a, b, c, right? Okay, so far I have a map. If I need to show it's an isomorphism, I need to show several things, right? So first of all, I need to show it's a linear transformation, right? And to show it's a linear transformation, what you need to do is you need to show that it satisfies the vector addition, right? It satisfies that vector addition is preserved, right? Okay, so how the statement of the preservation of vector addition is that T, if you have the vectors v1 and v2 inside p2, you add them first and then you apply T, right? That's the same as if you have your vector v1, you apply T. You have a vector v2, you apply T, and then you add, right? So in order to show that this map so far is a linear transformation, what we need to do is you need to show that the preservation of the vector addition holds, right? And this would be how you do it, right? So let's go through this, right? Okay, so I have T of a v1 plus v2, right? So what I'm supposed to do is I'm supposed to first add the vectors inside p2, which means I'm adding the two different polynomials. When I add the two different polynomials, what you do is you add the constant terms together, you add the coefficient of the t together, you add the coefficient of the t squared together, right? So this should be t squared. Okay, so you add the coefficients together, you get this polynomial, and then you apply a map now, t, right? When you apply a map t, right, what this map t is, it's converting your polynomial here into a row vector, right? And it does that by just taking constant term, putting it as your first component, taking your coefficient of the t, putting it as a second component, taking the coefficient of the t squared, putting it as a third component, right? Okay, but remember I want to eventually write this as tv1 plus tv2, right? So you notice what this is a sum of two vectors a1 b1 c1 and a2 b2 c2, right? And now each of these, right, a1 b1 c1, right, is actually the image of a1 plus b1t plus c1t squared under the map t, right? So if you want, you're going backward now from the R tree, you're now going backward to the polynomial, right? Okay, so likewise over here, this is the image, this a2 b2 c2 is the image of the polynomial a2 b2t plus c2t squared under the map t, and this is just tv1 and plus tv2, right? Okay, so what I showed over here is that the vector addition is preserved, right? And that is one condition. Remember, you also need to show that your linear transformation preserves scalar multiplication. Okay, and you can check that. It will be a little easier. It's same sort of idea as this work in here, right? And if you check that, you realize that this map T also preserves scalar multiplication, right? So the T is a linear transformation, right? But in order for it to be an isomorphism, the linear transformation needs to be one-to-one and onto, right? Alright, so in order to show that a linear transformation is an isomorphism, we need to show that as one-to-one and onto, right? So let's just recall your definitions of one-to-one and onto, right? Okay, so a function, right, such as these basic functions over here, right, it's going to be one-to-one, right? If it's going to be one-to-one if any element in your codomain, right, has at most one preimage, right? Okay, so for example, over here, this C here, it has one preimage, and that preimage is 3 over here, right? This A over here, it has one preimage, which is this 4 over here, right? Okay, and likewise, each of these over here has exactly one preimage, right? So this is injective here, right? This is one-to-one. Okay, so let's say consider this one here, right? this is also one-to-one, right? Because if I'm looking at this element over here, it has at most one preimage, which is this one over here. This one over here has at most one preimage. It doesn't have any preimages. That also satisfies the at most one, right? Okay, so this is one-to-one, but it is not onto, right? But it doesn't stop it from being one-to-one, right? And an example of something that is not one-to-one is this function over here, because if you look at the C here, the preimage consists of two elements in X, 3 and 4, right? So this C here does not have at most one preimage, right? It has actually two preimages here, right? Okay, so that's the idea of one-to-one, but your formal definition of one-to-one is, in fact, that we will use is that a function uh, is one-to-one if when you consider f of a is equal to f of b, right? So if I have uh, two elements in X, not necessarily different, right? And if they map to the same element, right? Then what that means is that A has to be equal to B, right? Okay, so this definition here, one-to-one, is probably not the clearest definition in the world, right? But it actually is useful when we want to, in fact, formally show that something is one-to-one, right? Okay, so it's probably easier to see a case where this does not hold, right? Okay, so let's consider, for example, this function over here, right? So I'm calling the function here small f, right? And I'm gonna show that this isn't gonna hold, right? And because it doesn't hold, your function isn't going to be one-to-one, right? So let's consider f of a and f of b, right? So here the a is equal to 3 and the b is equal to 4, right? So what I have is I have that the f3 is actually equal to f4, right? Okay, so the a in this case is 3, right? And the b is 4, right? And the f of a equal to f of b is actually equal to c, right? Okay, so f of a equal to f of b means I'm taking two elements over here, and f of a equal to f of b means that they have the same image, right? But in this case, f of a equal to f of b does not imply a is equal to b, right? Okay, so f of a equal to f of b, if it did imply a is equal to b, right, that would mean that the 3 is going to be the same as 4, right? But that's not the case over here, right? So in this situation, this is what describes the situation here with the 3 and 4 mapping to C, right? The f of a is equal to the f of b, right? The f of a, which is C, is equal to the f of b, which is C, right? But the equality of f of a and f of b, right, being equal to C does not imply that the a is equal to b. In other words, what you have is you have two different ones mapping to C, right? So this is what this means over here, right? If you have f of a is equal to b, implies that a is equal to b, right? Means that if I have possibly two things mapping, if I have two things mapping to the same element here, the only way that's going to happen if it is for one-to-one is that the two things would in fact have to be identical, and the a would need to be equal to b, right? All right. Okay, so this is your formal definition of one-to-one. Probably it's easier if you think of the contrapositive of this implication here. Contrapositive means that if I have an implication, right, contrapositive is of an implication is a logically equivalent statement for implication, where what you're doing is you negating statement Q, you're negating statement P, right? But you're reversing the direction of the implication, right? So P implies Q is logically equivalent to not Q implies not P, right? And what I have over here, what this is, this statement over here, this is the contrapositive of this one here, right? So contrapositive is f of a equal to f of b implies a is equal to b. The contrapositive of this implication is that a not equal to b implies that f of a is not equal to f of b, right? Okay, right. And this is easier to see see something as one-to-one using this here, right? Because a not equal to b, such as this one is not equal, such as this one is not equal to 2, implies that the images are not equal, right? If I have a not equal to b, so for example, if a is equal to 1 and b is equal to 2 and they're not equal to each other, then the images have to be different, right? And if that is true for all possible pairs of elements in your domain, right? If this statement is true for all possible pairs of elements in your domain, it means that your function is one-to-one, right? Okay, notice that this statement over here is not true for this case here, right? Because here I have two elements that are different, right? Okay, a is not equal to b, the 3 is not equal to 4, but that does not imply that f of a is not equal to f of b, because in this case over here, the f of 3 is actually equal to f of 4, right? So this over here fails this implication, right? Anyway. Alright, anyway, so this is what we will use to check to see if a function is one-to-one, right? This statement here, right? F of a equal to f of b implies a is equal to b. And then we also need to understand what onto is, right? Or surjective. Okay, so this is an example of a surjective function, right? Each element in your codomain has some element that maps it, has a preimage, right? So for example, this B over here has a preimage, which is 2, right? This C over here has two preimages, but that's okay, right? What we need is for onto is that at least it has at least one preimage over here, right? So each of these has a preimage, right? Okay. This here is not onto, right? Not surjective, because this C over here has nothing mapped into it, right? This C has no preimage, right? Okay, and how you state this formally, right? How you state that how you check to see if something is, you check to see if a function is surjective. So if I have a function from x to y, right? Well, it's surjective if all elements in the codomain, right? So if all elements in the codomain y over here, right, there exists at least one element in x such that that element maps to y, right? Okay, so for all elements in y, right, there exists at least one element in x such that that element maps to the element small y, right? Okay, all right, so this is a definition of surjective, right, which is handy to know. Okay, so this map that we were talking about from P2 to R3, right, defined by taking your coefficients of a polynomial and forming this row vector, right? We showed that it's a linear transformation, right? But what I want to do is I want to show it's an isomorphism between P2 and R3. So once I have that, and I'm sure there's a linear transformation already, so what's left for me to show is that it is one-to-one and onto, right? And then once I can show that the T is one-to-one and onto, then it's going to be an isomorphism, right? So first thing, let's check one-to-one, right? And remember what our definition of one-to-one is. What we're going to use is we're going to use this definition here, right? A function is one-to-one if f of a equal to f of b implies a is equal to b, right? And in our situation, for our notation, the function is big T, and the elements in the domain we denote as v1 and v2, right? So what we're trying to do is we're trying to show that if t v1 is equal to v2, then that implies that v1 is equal to v2, right? Okay, so let's do that here, right? So I start off with this equality here. TV1 is equal to TV2, right? V1 is just some element in the domain, and the elements in the domain are polynomials of degree 2, right? So V1 is I can express as A1 plus B1t plus C1t squared. V2 similarly I can express as A2 plus B2t plus C2tt squared, C2t squared, right? And now once I have this, I apply my map, right? And applying the map t over here means that I'm converting the polynomial into this row vector, and likewise I'm converting this polynomial over here into this row vector, right? Okay, so what does this mean over here? If this row vector is equal to this row vector, it means that the A1 is equal to A2, the B1 is equal to B2, and the C1 is equal to C2, right? Which means that your polynomials V1 and V2, right, they equal polynomials, right? Because A1 is equal to A2 now, B1 is equal to B2 from over here, and C1 is equal to C2, right? So what that means is that the polynomials V1 and V2 are actually equal to each other, right? Okay, so this shows that TV1 is equal to TV2 implies that V1 is equal to V2, and so T is 1 to 1, right? So notice you're using this definition over here, right? And it's easier to show something as 1 to 1, it's easier to probably use this definition than probably try to use this definition here, right? And we also need to show that this map here from P2 to R3, it's onto, right? But that's really just, it's fairly straightforward, right? So what you need to do is you need to show that for any row vector in R3, such as this ABC, right? There's something that maps to it, right? But there always is something that maps to it, right? For this row vector ABC, right? All you do is you just take the polynomial, right? A plus bt plus ct squared. This in fact is an element of P2, right? Because P2 are all polynomials of this form, right? And then the t of the a plus bt plus ct squared must map to the ABC, right? By definition, right? So anything that I have in R3, I could have anything, right? If this is, say, -1 here, and if this is 10 here, and if this is 2 here, right, then you'd always be able to find something in the domain that maps to it, right? Okay, right, so this over here, your map is obviously it's onto, right? Alright, so what we just showed is that if I have polynomials of vector space of polynomials of degree at most 2, like this polynomial here, and if I have R3, right, then P2 is isomorphic to R3, right? This map from P2 to R3 defined this way is a linear transformation, right? It's 1 to 1 and onto. So by definition, it's an isomorphism, right? And it's an isomorphism, and you also say that P2 and R3 are isomorphic as vector spaces. Okay, but an easy way in this case to see that the P2 and R3 are isomorphic is you want to realize that really they're just the same sort of thing, right? And they behave the same way because of the fact that you have 2, 3t, and t squared, right? The powers of t are just organizing the coefficients over here, just like how your components here are just organizing the 3 coefficients inside here, 3 numbers inside here, 2, 3, 5, right? And the vector addition does basically the same thing for P2 as it does for R3, and the scalar multiplication does the same thing for P2 and R3. You just need to relabel it slightly. If I have isomorphism from a vector space to itself, right? In other words, I have a linear transformation from a vector space to itself that is 1 to 1 and onto. So for example, well, vector space to itself means that the domain and the codomain are the same, right? Okay, so linear transformation from a vector space to itself, right? That is one to one and onto, right? In other words, the isomorphism from a vector space to itself, right? This has a particular name, right? I mean, you can call it an isomorphism, a vector space isomorphism. Nothing is wrong with that, but this sort of particular case, when the domain for an isomorphism, where your domain is the same as the codomain, right? This sort of isomorphism, you actually call it an automorphism, right? Okay, so an automorphism of a vector space is really just an isomorphism from the vector space, such as R2 to itself, right? And an example of an automorphism of R2, right, is uh, rotation, right? Okay, so this linear transformation, what it's going to do for me, it's going to rotate vectors by theta degrees in a counterclockwise direction about the origin, right? So, okay, so in this picture here, the blue vectors here are your vectors in the domain, right? So this here is vector I in the domain, and this here is vector j in the domain, right? The diagram just happens to show two vectors at the same time in the domain R2, right? If you want, we could focus on just the I over here, right? And what the red vector is the image, right? So that's going to be in the codomain, right? And what this is, you go from your I over here from this blue vector to the image vector by rotating by in this case 45 degrees, right? So if you want, we can see it here, right? So we're going to rotate, right? When you rotate your blue vector, when you rotate the blue vector, you're going to get a red vector, and the red vector is, if we rotate by 45, we get that, right? Okay, so right. Okay, so I'm starting off with this. This is the blue vector is in the domain, right? And I'm applying the transformation, right, which is rotation by 45 degrees. Okay, and the rotation by 45 degrees would take me from this blue vector in the domain to this red vector over here in the codomain, right? And likewise, what it'll do is it'll take this unit vector in the vertical direction. It'll take vector 0, 1, right? And it'll rotate it by 45 degrees in counterclockwise direction to give me this red vector over here, right? Okay, so this is this map over here. Any rotation matrix, in this case the rotation is 45 degrees, right? Is going to be an automorphism of a vector space R2, right? Okay, this over here would be a linear transformation, right? It'll be one to one and it'll be on two, right? This takes a certain amount of work to show, right? And we're going to see a little later on that you can tell that it's one to one and on two by looking at the matrix over here, right? And actually any linear transformation of this sort of form, right? Of this form vector, right? Which is x, so it's vector x times a matrix A over here. Any linear transformation of this, any map of this form would be a linear transformation, right? So any map of your form tx is equal to ax, right? This is a linear transformation. So that in fact will tell me that this is going to be a linear transformation, but we'd also need to check to see that it's one to one and on two, right? I won't show it in a general case, but we could always look at it in, say, a specific case. For example, when theta is equal to 90 degrees, right? So when theta is equal to 90 degrees, the rotation is actually, so I start back, say over there, right? The rotation is by 90 degrees. Okay, so, right, so this is when you start, right? This is, well, rotation of 0, right? But if you rotate by 90 degrees, you will get this over here, right? And this matrix here, right, is when you put theta is equal to 90 degrees into your matrix with the cos theta and the sin thetas and so on, right? So cosine of 90 is 0, cosine of 90 is 0 here, so you get 0 here and 0 over here. Sine of 90 is 1, and well, minus sine of 90 is minus 1, right? So this matrix over here, 0, 1, minus 1, 0, right? As a linear transformation from R2 to R2, right? What this is doing for you, it's rotating vectors by 90 degrees, right? In a counterclockwise direction about the origin, right? And this sort of linear transformation over here, this is an example of an automorphism, right? Okay, so while I said that an isomorphism such as this, right? Now, from P2 to R3, you could really just think of as a relabeling, right, of the elements, right? Where your relabeling will preserve the vector addition and the scalar multiplication. You could also think of your automorphism that way, right? But probably a better way to think of automorphism is as a rearrangement of your vector space, right? So, for example, here, when I'm rotating by 90 degrees, what I'm doing is I'm rearranging the vectors by 90 degrees, right? So let's look at this theorem over here, which says that any finite dimensional vector space over the reals, right, is isomorphic to Rn, right? Okay, and this is actually sort of nice, right? And in fact, we just saw an example of this, right? Okay, so P2, right? P2, a basis for polynomials of degree at most 2 is 1t and t squared, right? So P2 over here is a three-dimensional vector space, right? Okay, and being a three-dimensional vector space, this three-dimensional vector space P2 is in fact isomorphic to R3, right? So this over here, it's a finite dimensional vector space over reals, right? It on the surface doesn't really look like Rn, right? But it actually is isomorphic to R3, right? Okay, so the good thing about that is really all your properties, and so for example like the subspaces and the behavior, so like intersection of the subspaces and so on, really they just correspond to the subspaces in R3, right? So your behavior in R3 really just determines the behavior in P2, right? And so what this means is really if you have finite dimensional vector spaces over R, the fact that they all just isomorphic to Rn means that if you really want to, say, study finite dimensional vector spaces, all you need to do is really finite dimensional vector spaces over R. All you need to do is just study Rn, right? This Rn over here is your prototype, which will basically give you all your information and all your theory, right? For finite dimensional vector spaces. So really, this is a nice sort of result, which, as I said, means that your study of finite dimensional vector spaces will really just reduce a study of vector spaces of the form Rn here, right? Okay, so how do you get this isomorphism, right? Well, how you get this isomorphism is as what we did over here, right? Okay, so what you need is, in order to get your isomorphism, you need a map that will take you from your vector space to Rn, right? And for example, this is a map that will take me from my vector space P2 to R3, right? And well, how do you define the map, right? Well, it's a map on elements in my vector space, right? So the elements in the vector space, such as this a plus bt plus ct squared, right? What you need to do is you need to map it an element of Rn, right? In this case, it's R3, right? And an element of Rn is just really a row vector over here, right? Now, how can you map from a finite dimensional vector, an element from a finite dimensional vector space to a row vector, right? Well, one way of doing it is really to just take the coordinates of your vector, right? If you want the abstract vector space like P2, take the coordinates of it with respect to some basis, right? For example, over here, if I take the coordinates of a bt plus ct squared with respect to the basis 1 t and t squared, right? it means I'm writing a plus bt plus ct squared as a linear combination of the 1t and t squared, right? But it's sort of trivial over here because it's already written as a linear combination of 1t and t squared, right? Okay, so the coordinates in this case would just be the a, b, and c, right? This is a fairly simple case, right? But the point is, if I have any vector space V, finite dimensional vector space, once I have a basis for it, right, I can always just find the coordinates, and the coordinates would be a row vector that belongs to some Rn, where n is the dimension of this finite dimensional vector space, right? So this would be how you define the map, right? And I have it. Right, I really, I say the same thing over here in this proof, right? I have my vector space V. I have a basis for that vector space, right? And any element U in this finite dimensional vector space, what I do is I write the U as a linear combination of the basis elements, right? And the coefficients in that linear combination are the coordinates, right? So that is what maps me from any vector u in v, right, to coordinates, right, in Rn, right? Okay, so that's how your map is going to be defined by taking coordinates of your vector, right, with respect to some basis to get you, say, like a row vector like this, right? And then what you need to do is you need to, once you get that map, you need to show that the map is a linear transformation, which is what I do over here, right? And then you need to show that the map is 1-to-1 and on-to, right? Okay, which is done over here, right? So really this here, this example is illustrating how this proof over here would work, right? Okay, so this is nice to know, is pretty interesting, right? That basically any finite dimensional vector space V over the reals, right, is really just isomorphic to Rn, where the small n is the dimension of your finite dimensional vector space V. Okay, so in this section, what we want to do is we want to represent any linear transformation by a matrix, right? Well, any linear transformation between finite dimensional vector spaces, right? Okay, so before I get into the representation, we need some preliminary results, right? Okay, so if I have a linear transformation from Rn to Rm, right, defined via matrix multiplication, so this x over here is a vector in Rn, right? And how you get the image of this vector x under the map T is you just take a vector x and you multiply it by a matrix A, right? Okay, so an example of a map that is of the form Tx is equal to Ax is this map over here, right? So the vector x is a vector in R2, and what you're doing is you're taking a vector x, you're multiplying it by 2 by 2 matrix over here, and you're going to get a vector in the codomain, right, in your target vector space, right? And in this case, this particular example, right, the vector in the domain, right, under this map, what you're doing is you're rotating it by 90 degrees counterclockwise about the origin, right? Okay, so this is an example of a linear transformation of a map of the form Tx is equal to Ax, right? Okay, next example of from a map from Rn to Rm, I noticed that these are no longer the same vector spaces, right? So this is R3 and this is R2 over here. Your domain is R3 and your codomain is R2. Okay, is a next example of a map of this form Tx is equal to Ax is this example here, right? And notice the size of your matrix, right? In order for your matrix multiplication to be well defined, you'd need 3 columns over here, right? 1, 2, 3, in order to match the 3 rows in this row vector, right? And because you map in from R3 to R2, in other words, the result is going to be a 2-dimensional vector. That would mean that you're going to have 2 rows in this matrix, right? So the size, if I map in from R3 to R2, right, using matrix multiplication AX, right? What that means is that your matrix A over here, number of rows is equal to M, right? And then the number of columns of your matrix is equal to the N over here, right? All right, so let's show that a map of this form Tx is equal to Ax, right? This, in fact, is a linear transformation, right, from Rn to Rm, right? Okay, in order to show that it's a linear transformation, you need to show that it preserves vector addition and it preserves scalar multiplication. And in this case, the proof is pretty easy, right? Okay, so we need T of x plus y, right? So what that means is we're going to multiply x plus y by a matrix A here, right? Now, when you have matrix multiplication, well, this is a matrix multiplied by a sum of vectors, right? Or, well, the vectors you can also regard as matrices, right? So a sum of matrices. Then what I'm doing is I'm using a property of matrix multiplication over here. That if I have matrix A times a sum of matrices, it's A times your first matrix and then A times your second matrix, right? Okay, so this is a property of matrix multiplication or matrix vector multiplication, right? Which is in fact shown in the notes. You could take a look at lemma 3.10 if you're interested in the proof of it, right? Okay, and anyway, so at this point, what I have is I have ax plus ay, right? But ax is just t of x, right? Because remember, to calculate t of x, you multiply x by a, right? And similarly, ay is just ty, right? So what I get is t of x plus y is equal to tx plus ty, right? So I get that the vector addition is preserved, right? And to show the scalar multiplication, we consider t of cx, right? So you're multiplying cx against the matrix A, right? But then a next property of matrix multiplication is I can just pull the scalar out in front here, right? And I have c times ax, and the ax is just t of x, right? So I managed to pull the c out of the tx over here. I pull the c out over here, so I get t of cx is equal to ctx, right? So the scalar multiplication is preserved. Alright, so if I have a linear transformation from Rn to Rm expressed in this form, matrix multiplication A times x, this is useful because what I can do is I can use the columns of this matrix to tell me, to give me certain facts about my linear transformation, right? Okay, so columns of this matrix, it's 2, 1, and 2, 1, right? Okay, so your linear transformation from Rn to Rm expressed as t of x is equal to ax, right? It's going to be onto if and only if the columns span the Rm, right? So in this case, the Rm is R2, right? Okay, so if and only if your columns span the codomain, right? Now, if I look at these columns here, right, 2, 1, and 2, 1, right, these actually do not span R2, right, because this vector over here is the same as this vector here, right? Right, and the span of these two vectors turn out to really just be the span over here, span of a single vector 2, 1, right? And that the span of a single vector isn't going to get you the entire R2, right? So, well, what's okay, vectors. So remember what this means, right? Span of vectors 2, 1 means all linear multiples of your vector 2, 1, and it doesn't make a difference if you have a second one, because if you use a multiple of 2, 1 over here, right, it's still going to be a scalar multiple of 2, 1, right? So the span of these two over here, right? Okay, so the span of your two vectors 2, 1 is still just going to be equal to the span of 2, 1, right? And this here would be all vectors that are parallel to your vector 2, 1 over here, right? These would be positive multiples of your vector 2, 1, and these would be on the side. This would be negative multiples of your vector 2, 1, right? So all possible multiples of your vector 2, 1 lie along this line, y is equal to x on 2, right? And you notice that is not the entire plane, right? This is only going to give you a line in the plane, right? So your span of these two vectors over here is not R2, right? Right, so for this linear transformation, looking at the columns of your matrix A, right, your columns do not span R2, do not span your codomain, right? So from that, you can tell that this linear transformation over here, according to this theorem, right, if your columns, okay, so T is onto if and only if the columns span the codomain, right? And in our case, the columns do not span the codomain. So if the columns do not span, and this is an if and only if statement, what that would imply is that T is not onto, right? So over here, what we can say is that this linear transformation here, it is not onto because the span of your columns is not equal, doesn't give you the whole of R2, right? Okay. And okay, so just by looking at the columns, you can tell the columns of this matrix A, you can tell if the linear transformation is onto, right? But remember, we did this example previously, right? In a previous video, we worked out what the range space is of this linear transformation. And the range space of this linear transformation actually is the span of your vector 2, 1, right? Okay, so we can see, if we want to look at it that way, that and we saw a graphic illustrating that, right? This over here, this is the range space, right? Your range space are all vectors that lie on your line y is equal to x on 2, are all vectors parallel to 2, 1. And you notice that this is your range space over here, and if this is the range of your linear transformation, and the range of your linear transformation, it's only gonna lie on this line, right? Well, you're not picking up any vectors that do not lie on this line, right? Okay, so what we get out of the calculation for your range space of your linear transformation being this vectors that lie on this line, right? This is saying that, well, okay, if your range is just going to be vectors lying along this line, you're not picking up any other vectors in R2, right? So just looking at your range space over here, you see that the range space is not on 2, right? Okay, so we could have done it that way. We could have calculated the range space, right, and check from the range space to see if the linear transformation was onto, right? But this way, by looking at the columns, it's actually faster, right? You take your columns of your matrix, assuming that your linear transformation is in this form, T of x is equal to ax, right? You take your columns of your matrix A, and if these columns span your codomain, which in this case is R2, right, then the linear transformation would be onto, right? But as it is, the columns do not span, and because the columns do not span, this linear transformation is not onto. Alright, the second result that we have in this theorem is that by looking at the columns again, right, we can determine if the linear transformation is 1 to 1, right? And what we check for now is to check to see if the columns of your matrix A over here, if they're linearly independent, right? So let's use this example again. All right. Okay, so this is my linear transformation. In this case, the matrix A is this one with your first row being 2 and 2, and your second row being 1 and 1, right? Your columns here are 2, 1, 2, 1, right? And if you look at your columns here, these two columns are not linearly independent, right? Clearly, because, well, one is just multiple of the next one, right? Well, one is actually identical to the next one, right? So these are not linearly independent, right? So therefore, according to this theorem, your linear transformation T is not 1 to 1, right? Okay, and we can actually check that more directly. So remember, this is my linear transformation over here. What I'm going to do is I'm going to show that it is not one-to-one more directly, right? All I need to do is I just need to find two vectors with the same image, right? Two different vectors with the same image. And if I consider, for example, your vector 1 minus 1, right? The vector 1 minus 1, well, 1 minus 1, this vector is in a null space, right? So it will in fact map to the 0 vector, right? And the vector minus 1, 1, right, also is in a null space, so it maps to the 0 vector again, right? Or you could just work it out here, right? A times this vector 1 minus 1 will give you 0, 0. And A times the vector minus 1, 1 will also just give you a 0 vector here, right? And notice both of these, right, 1 and minus 1, and minus 1 and 1, which are two different vectors, they map to the same thing, right? So that tells you that your linear transformation is not one-to-one, right? Okay, so what I'm doing there is I'm checking it directly, right? But according what this theorem is doing for you is you could really just look at the columns, right? Okay, so here for your linear transformation of your form t of x is equal to ax. If you look at the columns and the columns are not linearly independent, then your linear transformation is not one-to-one. If, however, the columns were linearly independent, then it would mean that your linear transformation is one-to-one, right? And let's see an example of that. All right, before we look at the example, let's just look at the third part of this theorem, right? So here what we did is we checked to see if the columns span, and if the columns span, it would mean that the linear transformation is onto. Here what we do is we check if the columns are linearly independent, and if the columns are linearly independent, that would mean that the linear transformation is one-to-one, right? And what this third one is a combination of 1 and 2, right? Okay, so if your columns now form a basis, right? And remember what basis means, right? Basis means that it's supposed to, a basis for Rm means that it's supposed to span Rm and also be linearly independent, right? Okay, so this one says that if it is a basis, right, if your columns form a basis for Rm, then what you're going to do is you're going to have these two conditions being satisfied, right? In other words, T is going to be onto and one-to-one, right? And you want to remember that a linear transformation that is onto and one-to-one is called an isomorphism, right? So really this third statement over here is really, if you want, combining statement 1 and 2 over here. Okay, so let's consider this linear transformation now, right? Which is different from the one that we just had, right? It's still a map from R2 to R2, right? But it's a different map, right? This map over here, we saw already, this is a rotation of your vectors counterclockwise by 90 degrees, right? Okay. Right, so now, well, what are the columns of this matrix here, right? Notice this linear transformation is of the form Tx is equal to Ax, right? Your columns would be 0, 1, first column is 0, 1, second column is minus 1, 0, right? And you want to notice that these columns here, these are linearly independent, right? Okay, because, well, they're not multiples of each other, right? Okay, you have two vectors that are not multiples of each other, and then it's linearly independent, or you could check formally using your definition of linear independence. Anyway, so these two are linearly independent, and these would also actually span R2, right? It'll probably take a little bit of work, but remember when you calculate and span, what you're doing is you're taking linear combination, all possible linear combination of these two vectors, right? Okay, so if you're taking linear combinations of the minus 1, 0, it really doesn't make a difference that you have a minus over there in this case, right? Because you could always just adjust your scalar, just take the negative of your scalar, right? So what you're doing over here is you're really just taking a linear combination of standard basis vectors, 1, 0, and 0, 1, right? And those will span R2, right? Or you could check more formally that these are going to span R2, right? It takes a little bit of work if you want to write out, do all the work in, right? Anyway, so these two will span R2, span the codomain, right? So what do I have? I said that they're linearly independent, and because they're linearly independent, they're going to be, your linear transformation is going to be 1-to-1. Okay, and because it spans your codomain R2, right? Because your columns span codomain R2, it means that your linear transformation is going to be onto, right? And therefore, what you're doing is you're now actually in condition 3 over here, right? These columns are linearly independent and they span R2, right? So therefore, these are basis for R2. So because your columns here are basis for R2, it means that this map T, it's an isomorphism, right? Okay, and remember I stated that, but I stated it without proof, right? So this is an isomorphism, a linear transformation that is 1-to-1 and onto is an isomorphism. And well, in the specific case, when the domain and the codomain are the same vector spaces, then you also call this an automorphism, right? But that doesn't stop it from being an isomorphism. Any automorphism is an isomorphism. Alright, so we saw if a linear transformation from Rn to Rm can be expressed in a form Tx is equal to Ax, right? In other words, it's a column vector and then multiplied against a matrix here, A, right? Then by looking at the columns, we can determine if the linear transformation is 1-to-1 and onto, right? So having your linear transformation expressed in this sort of way, it's good, right? And this a linear transformation of this form, right? Your matrix A here is said to represent your linear transformation, right? Because it's carrying information about the linear transformation, right? Okay, so A here is, so in this case, 0, -1, 1, 0, right? This matrix here represents your linear transformation T, right? Okay, so this sort of expression T of x is equal to Ax, as I said, it's useful, right? By looking at the columns. Okay, you can determine if the linear transformation is 1-to-1 and onto, right? However, let's consider this this linear transformation here, right, from R3 to R2, right? It's given in this form, right? And we actually showed that this was a linear transformation previously in our last video, right? Okay, and it's done in the notes also as well, right? If you want to take a look in example 6.2, right? So this is a linear transformation, but you want to notice that this actually is not expressed in this form, right? Tx is equal to Ax, right? So you're not seeing your matrix A, you're not seeing that linear transformation expressed in the form T of x is equal to Ax, right? But actually, any linear transformation from Rn to Rm, right? You can always actually write it in the form T of x is equal to Ax, right? Okay, so that is what I'm stating over here, right? Any linear transformation from Rn to Rm, such as this one over here, right? I can find a matrix A such that I can write this linear transformation as T of x is equal to Ax, right? Okay, and such a matrix A is said to represent your linear transformation, right? Okay, so how can we do that, right? So this is my linear transformation over here, and what I want to do is I want to find the matrix, right? Okay, so I'm going to do it this way over here, but what I will do in a little while is I'll show you a faster way how to get it, right? Okay, so I have T of x1, x2, x3, right? Now, what you're doing is you're taking the image of your the vector x1, x2, x3 under the map T, right? Now, x1, x2, x3, I can write this way as x1, 0, 0, 0 plus 0, x2, right? Plus 0, 0, x3, right? Okay, it's not hard to add these three and realize you're going to get x1, x2, x3, right? Right, now what you're going to do is, okay, so next thing I'm going to do is I can actually take out the scalar x1, x2, and x3 from each of these, right? And now that I did that, what you want to notice is that these are standard basis vectors, right, for R3, right? So let's just notice that, right? Anyway, so I have this vector x1, x2, x3 written in this form now, right? I didn't really change anything because all I did is just rearrange how I wrote the vector x1, x2, x3. And now what I do is I'm going to and now what I'm going to do is I'm going to use a property of a linear transformation that the linear transformation preserves vector addition, which means that I can split this sum up, right? And I also use the fact that it preserves scalar multiplication, which means I can pull the scalars out, right? Okay, so this sum over here will split like this, right? And then I'm going to pull the scalars out, so I pull x1, x2, x3 out, right? Okay, so what I get is that the image of x1, x2, x3 under the linear transformation t is equal to this, right? And now what I'm gonna do is I'm gonna work out what the t100 is, and the t010 is, and the t001 is, right? Okay, so what is t100, right? That's not hard to work out. All you're doing is you put in 1 over here, 0 in here, and 0 in here. And what you'll get is 2 on top, and you'll get 0 below, right? Which is this 2, 0, right? And similarly, I could work out t010, right? So that's when x2 is equal to 0. And I'll get 0 on top and minus 4 below. And then finally, 001, right? So I'd have 0, 0, and then the x3 is equal to 1. So I'd get 1 on top and 0 below, right? Which is this, right? Okay, and here I have this over here, right? Now you want to recall, and we talked about this already, right? If I'm multiplying a matrix here by a column vector such as x1, x2, x3, right? How I can work this out, it would be x1 times your first column plus x2 times your second column plus x3 times your third column, right? You could take a look at lemma 3.9 if you want to see a proof of this, right? Or you could also check, just expand out this second line over here, expand the third line, and you'd see that you get the same thing, right? Anyway, so the point is, if I notice here, I have the scalar times column vector plus the scalar times the column vector plus the scalar times this column vector here, right? So I can go from this sort of expression to a matrix multiplication, right? Where the columns of this matrix are the 2, 0, the 0 minus 1, the 1, 0, right? Okay, and notice finally, this is what I want, right? This is a matrix A over here times a column vector, right? So what we have is that T times this column vector here is equal to A times this same column vector, right? So what I just showed is that this linear transformation I wrote in the form T of x is equal to AX, where your matrix A is the T0, 0 minus 4, 1, 0, right? Now, one thing you want to notice is that these column vectors here, how are you getting them, right? You could go through this process, but a fast way to get your column vectors is really you taking the image of your basis vectors, right? So, and the basis vectors that I'm using over here are standard basis, right? So if I take standard basis vectors 1, 0, 0, right? I take the image of that, right? That would give me the 2, 0, right? So that would be the first column. Take the second basis vector, take the image of that, that would give me the 0 minus 4, right? And take the third basis vector 0, 0, 1, right? Take the image of that, and that would give me the 1, 0, right? Now remember, these are basis vectors. The 1, 0, 0, the 0, 1, 0, and the 0, 0, 1 are basis vectors, standard basis vectors for R3, right? So in order to get your matrix A, right, what you're doing is you're taking your standard basis vectors for R3, right? You taking the images of those, right? So you're mapping them under T, right? And the answers that you get, like this 2, 0, what you're doing is you're using it to form your columns of your matrix A, right? Okay, and why you'd want to do that? If you have this linear transformation given like this, and you write it in the form T of x is equal to AX, right? Why you'd want to write it in this form is, remember, you can use the columns to give you information about the linear transformation that you probably wouldn't be able to see from here directly, right? Okay, so from your, notice these three columns here, right? The 2 0, the 0 minus 4, and the 1 0, right? Those three columns are not linearly independent, right? They they're columns in R2, right? And once you have the vectors in R2, and once you have three vectors in R2, and R2 is a two-dimensional space, three vectors in R2 must be linearly dependent, right? So your columns here are linearly dependent. So just by looking at the columns, you can tell that this linear transformation is not one-to-one, right? And you can also check that these columns here, they're going to span R2, right? They're going to span this codomain, right? So what that tells you is that this linear transformation is onto, right? Okay, so that is essentially why you'd want, if you have a linear transformation, why you'd want to write it in this sort of form: T of x is equal to ax. This matrix A, or more specifically the columns of the matrix A, will tell you if your linear transformation is one-to-one or onto. Okay, and here we have this result that if I have a linear transformation from Rn to Rm, right, I would always be able to write it in this form: T of x is equal to Ax, right? So I'd always be able to find a matrix A such that this linear transformation I can write as T of x is equal to Ax, right? And the proof of this theorem really uses the working in this example here, right? So in order to find your matrix A, what you do is, if you wanted to prove it, right, if you wanted to prove the theorem, the vector in Rn, right, which in this case is x1, x2, x3, right, because this is R3, right, you would split it this way, right, and then using the splitting and using the properties of the linear transformation, you write it like this, right? And then these, the images of your basis vectors for images of your standard basis vectors for R3, right? Those are going to form the columns of your matrix A, right? Well, that's actually constructing the matrix, right? This actual working over here, I actually showed that the T of x is equal to A of x over here, right? And the proof of this theorem really follows this sort of justification here. Alright, so linear transformation from Rn to Rm I can always write as Tx is equal to Ax, right? So I can find a matrix A that represents my linear transformation, right? But what about if I have a linear transformation that is not from Rn to Rm, right? So for example here, I have vector space of matrices here, right? And here I have a vector space of polynomials. And I have a linear transformation defined from matrices here to the polynomials, right? Okay, so this one is not Rn and this one is not Rm, right? Okay, so for this sort of situation, I can also get a matrix that represents this linear transformation, right? So that's what we want to look at now. Alright, so we're looking at this sort of situation here where I have a linear transformation between vector spaces, and these are finite dimensional vector spaces, right? But these are not Rn and Rm, right? Okay, but I still want a matrix to represent them, right? So in order to do that, what I'm going to do is I'm going to use this result over here, right? Okay, so I have a linear transformation from V to W, right? So an example of V is this M2 to R here. An example of W is this P2 here, right? Okay, and in order to get a matrix representing this linear transformation, what you would need is you would need some fixed basis, right, for your domain vector space, and another basis, right, for your codomain vector space, right? So that is what this is saying here with respect to fixed bases for V and W, right? So you need a basis for your domain and you need a basis for your codomain, right? You can represent your map, right? In this case, the map is F by a matrix A, right? Right, now how you actually do that, it is the proof of this is probably a little bit on the complicated side, right? So I'm not going to go through the details of the proof. I'll just give you a rough idea how it works, right? Okay, so here what I have is a map between vector spaces V and W, right? But up here, right, what this result over here said is that if I have a map between Rn and Rm, right, I can always represent it by a matrix A, right? I can always write it in this form: T of x is equal to Ax, right? Okay, so the idea over here is that, and we saw previously that any finite dimensional vector space is isomorphic to Rn, right? So the idea for getting the matrix representing something like this, right, is you're gonna use an isomorphism for the V here. You're going to use an isomorphism for the W over here, right? And you're gonna use it like that, right? Okay, so right, so I have my V and I have the W, and what I'm going to do is I'm going to use an isomorphism from V to Rn, right, which exists, right, which was a statement of the theorem that I just showed you. And you're also going to have an isomorphism from W, right, from the codomain to Rm, right? Okay, so once you have those two isomorphisms, right, what you could do is you could form a construction like this, right? Okay, so this is your linear transformation, right, from V to W, right? Okay, so from V to W, and this T over here is to indicate that the linear transformation is called T, right, which is just a different notation from what I have here, right? Okay, so given this linear transformation, remember this one is not Rn or Rm, right? Okay, what you do is you use the isomorphism from V to Rn, right? Now, what you do is you in fact use the inverse of that isomorphism, right? Okay, so you notice this isomorphism called RV maps from V to Rn, right? What you want is something that maps from Rn to V, right? So you take the inverse map, right? It's really just the inverse function, right? From Rn to V, right? And then you have the isomorphism from the codomain to Rm, right? Okay, and the idea now is that the composition of these, right, is actually a map from Rn to Rm, right? And a map from Rn to Rm, we saw already, has a representation as T of x is equal to Ax. In other words, we'd always be able to find the matrix A. We'd always be able to write a map from Rn to Rm in this form here, right? In other words, we'd be able to find the matrix A, right? So that's the idea of how this theorem works, right? The linear transformation from V to W, right? You can use isomorphisms from V to Rn and from W to Rm, right? Using those isomorphisms, you can rewrite this linear transformation as a linear transformation from Rn to Rm. And the fact that these are isomorphisms, the RW and the RV isomorphisms, doesn't really change the properties of this, doesn't change the properties of this linear transformation. By properties, I mean that if this one is on 2, then this one is going to be on 2, right? And if this one is 1 to 1, this one is going to be 1 to 1, right? So that's the idea here, right? That's how we actually going to get that's how you construct the matrix theoretically, by using this sort of composition over here, right? But what I'll do is I'll give you just an algorithm for finding the matrix that represents a linear transformation such as this, right? And the algorithm really is just this statement over here, right? To get the matrix A, right? The jth column of your matrix A is your coordinate vector of the image tvj, right, where vj is the jth basis vector of bv, and bv is a basis for v here, right? Okay, so what you're doing is you're going to take your basis vectors from your v over here, right? you're going to take the image of those, right? And then get the coordinates of these here, of the image vectors, right? With respect to the basis of W, right? So you need to use both bases, right? You need to use the basis for V, right? And you need to use the basis of W, right? When you're taking coordinates, right? Okay, so it's probably easier if you see an example of how this works, right? All right, so this is my linear transformation from 2 by 2 matrices to polynomials of degree at most 2, right? And this is how the map is defined, right? Your 2 by 2 matrix, which is A, B, C, D, right? What you're doing is the constant term in your polynomial is going to be A plus B plus C, right? And then the term in D squared is going to have coefficient D over here, right? Okay, so you're using the entries in this 2 by 2 matrix to form your polynomial over here, right? And this is what the map is, right? So for any matrix, any 2 by 2 matrix in your domain here, right, you would have a corresponding polynomial in the codomain, right? Okay, now what we want to do is we want to get the matrix that represents this linear transformation, right? Okay, so how do we do that? As I said, what you're going to do is you're going to be using a basis for your domain and you're going to be using a basis for your codomain, right? So both of those are given to you in the problem or given to you somehow, right? Okay, so right, so over here in part 2, right, they tell you to, in fact, what the bases are, right? That the basis for your domain is these 4 matrices over here, right? Okay, and you should know by now that this 2 by 2 matrices form it's a 4-dimensional vector space, right? Okay, so your basis has 4 vectors in it, right? 4 elements in it. Okay, so this is going to be your basis that we're going to use for the domain, and they say to actually use this basis here for the codomain, right? And P2 polynomials of degree at most 2 is a 3-dimensional vector space. So your basis here has 3 elements in it, right? Okay, so we're using, this is the basis for the domain and this is the basis for the codomain, right? And over here, this really says the same thing as what I was saying earlier in my notes, right? Okay, what I'm saying here, using the basis vectors, right, and to form the columns of the matrix A, this statement here is the same as the statement. The statement here, I just changed the notation to match the notation in the problem, right? Specifically, I'm calling a linear transformation F over here instead of T, right? Anyway, so how do you form the matrix A, right? Well, how you form it is via columns, right? Okay, so, well, you want to get your first column, right? So to get your first column of your matrix, what you do is you take your first basis vector here, right? So your first basis vector is 1, 0, 0, 0, right? So you take your first basis vector from your domain, right? First basis vector is 1, 0, 0, right? And then what you do is you apply the map to it, right? So the 1, 0, 0, we apply the map to it, right? And when I apply the map 1, 0, F to 1, 0, 0, right? Well, the A is equal to 1 and everything else is 0, right? Which means I'll get a 1 over here for the A and then 0 everywhere else. In other words, when I apply the map, I will just get, when I apply the map F to 1, 0, 0, I will just get 1 over here, right? Okay, right. Okay, so that is this over here, right? That's the image of your first basis vector, right? But to get the columns, what you would need is the coordinate vector, right? You want the coordinates of 1 with respect to this basis in P2, right? Okay, so what's the coordinates of 1 with respect to this basis, right? I wrote it on over here, right? So if I have 1, right, I can write it as a linear combination of these basis elements, 1, t and t squared, this way, right? So your coordinates of 1 would be 1, 0 and 0, right? There's only one way to remember your coordinates for a given basis. It's unique, right? So there's only one way to do this, and you want to make sure that you use the order that's specified for your basis, right? So I have 1 0 0, right? So these are your coordinates 1 0 0, right? 1 0 0 are the coordinates of 1 0 0 are the coordinates of your image of your first basis vector. So this is the image of the first basis vector. The image of the first basis vector turns out to be equal to 1, and the coordinates of 1 with respect to your second basis, which is the basis for the codomain, right? Coordinates for that is 1 0 0, right? Okay, so what that means, I notice I have a transpose over here. These coordinate vectors, you want to write them as columns, right? So this 1 0 0 is going to be the first column for your matrix, right? To get your second column for your matrix, you now use your second basis vector here, right? So your second basis vector from your domain, right? What you do is you take the image of that, right? When you take the image of that, you'll get, in this case, the b is 1 and everything else is 0. In this case, what you'd get is 0 here, 1 here, 0 here, and 0 here. So again, you're going to get 1, right? Okay, so image of a second basis vector is 1. Coordinates, it will have the same coordinates, right? And this coordinate vector is now going to form your second column, right? So your first column over here came from the first basis vector. Your second column over here is going to come from your second basis vector, right? And the third column you're going to get by using the third basis vector, right? Okay, so do the same thing, right? You apply f to this third basis vector, and you're going to get, right? In this case, the a is 0, the b is 0, the d is 0, but the c is equal to 1, right? So what you're going to get is 0 here, 1 here, and then a 0 here. So again, you're going to get, in this case, the image of this third basis vector is equal to 1, right? It isn't always, you're not always going to get the same thing like this, right? This is just happening because of what this map is, right? Okay, right. So, and then the coordinates of this one again is 1 0 0. So this is using your third basis vector, and therefore this here is going to form your third column, right? And then finally you have your fourth basis vector. You take the image of that. In this case, it's only the d that is 1, the a, the b, and the c is 0. So your image of 0 0 1 under f over here is now going to be t squared, right? So it's different now, right? And the coordinates of t squared with respect to your given basis, your codomain, right? The coordinates of t squared, you can actually see it here, right? The coordinates of t squared, you express t squared as a linear combination of the 1, the t, and the t squared. And there's there's a unique way to do that, right? So it's 0 here, 0 here, and 1 here. So your coordinates are now 0 0 1, right? Okay, so therefore the right your fourth column here is 0 0 1, and that came from using your fourth basis vector, right? Okay, so this is how you construct your matrix, right? That's an example of how you construct your matrix, right? What you're doing is, and it's summarized over here. Okay, you take your basis vectors for the domain, right? And that's given to you over here. You take your basis vectors for your domain, and then starting with the first one, you take the image of your first basis vector under your map. That gives you some element, and this element here, that gives you an element in P2, right, in the codomain. So what you want is the coordinates of this element in the codomain, right? And the coordinates of this element, which is 1 0 0, would form your first column, right? And similarly, your second basis vector, you take the image of that, right? Take the coordinates with respect to the basis for the codomain, and those coordinates would form your second column vector, right? And that is how you form this matrix. You really form it column by column by using your basis vectors here one by one. There's a fair amount of work to get this matrix representation, right? And what can you use this matrix representation for, right? Well, you can use the matrix representation for matrix A representing a linear transformation of the form Rn to Rm, right? And remember, in this case, what you're doing is you're looking at the columns of A, right? If the columns of A span the Rm, right, then your map T is onto, right? If your columns are linearly independent, then your map T is 1 to 1, right? And if your columns form a basis for the Rm, then the T is an isomorphism, right? So you have a similar result in this case here. When you have vector spaces that are not Rn or Rm, right? Again, you can use the matrix A representing the linear transformation to determine if the linear transformation is 1 to 1 or onto, right? Okay, and how you do it is you look at your columns of your matrix, right? And you want to see if, for example, okay, so you want to see if your columns span Rm, right? And the M over here is the dimension of this vector space W, right? Or next way to look at the M is the number of rows in this matrix here, right? Okay, so if your columns of A span Rm, right, then your linear transformation is onto, right? If your columns are linearly independent, right, then your linear transformation is 1 to 1, right? And if your columns are both linearly independent and span Rm, right, in other words, if they form a basis for Rm, then this map is an isomorphism, right? Okay, so let's look at this example here and let's see if we can figure out if it's 1 to 1 and onto, right? If it's 1 to 1 or if it's onto. So the columns of this matrix A are not linearly independent, right? Once you have the column vectors repeating like this, that is telling literally, well, that your columns are not linearly independent, right? Because once you have a vector that is a multiple of the next one, right, then the vectors are not going to be linearly independent. But I actually show it over here, right? Okay, so I actually give a non-trivial linear relationship among your column vectors over here, right? Right, so I actually find a non-trivial linear relationship among your columns of your matrix A, right? And you want to notice that if I have 1 times your first column plus minus 1 times your second column, and I use 0 times the third column and 0 times the fourth column, this over here will add to the 0 vector, right? So this non-trivial linear relationship among your columns over here tells you that your columns are linearly dependent, right? Because your columns are linearly dependent, what that means is, according to this result here, right? Because your columns are linearly dependent now, your map is, your linear transformation is not 1 to 1, right? And that's what I state over here, right? Your linear transformation is not 1 to 1, right? Okay, and next thing too is you want to see if these columns here, if they span R3, right? And what you want to notice is that, well, I actually stated formally over here. This column vector 0, 1, 0, right? So 0, 1, 0 will never belong to the span of these 4 columns, because I'd never be able to pick up this 1 over here from these columns, because for these 4 columns the second component is always 0, right? And I'd never be able to get this non-zero 1 over here, right? Okay, so this 0, 1, 0 is not in the span of these columns. It's not in the column space of A. and therefore the columns do not span R3, right? And because your columns do not span R3, that tells you that your map is not onto, right?